And it's my great pleasure to introduce Zhang Shao, who's leading the CertiCost project at Yale. You heard a little bit about CertiCost already from Ronghui. Good. And Zhang is going to give us more detail. And I don't know, you also want to mention the crypto session tonight?
Sure.
Sort of shortly after 7.
Yeah. Okay. It's my pleasure to be here. So Ronghui has given a nice introduction yesterday about CertiCost. So I'm going to talk more today about ongoing research projects related to CertiCost and what we have done in recent years or in the last year or two. Just a reminder that Leonard has sent a message to you guys this morning regarding a cryptocurrency session at 7 p.m. I think it's in different room, right? In this room, actually?
Here, yeah.
Oh, okay. So Vitalik Buterin from Ethereum Foundation will be here, talk about how Ethereum work can benefit from work like DeepSpec. So hopefully some of you are interested in attend. Okay, so what I'm going to do today is to say a little bit more about a high-level methodology done in the CertiCost group, and then I will dive into some of our recent work on how we actually verify concurrency, okay? So at the very high level, the line of research we do for CertiCost is really try to solve the essential problem that the peer researcher have been trying to address. That is, we want to write the best software. We want to uncover the essence of these various software system, hardware system, all these so-called system of systems. There are ways to build these systems in informal, quick and hacky and dirty ways. But if you want to actually prove something correct at a larger scale, then you have to at least get the high-level structure right. You have to understand the system component by component, understand their interaction, understand how things are composed together. That's what I mean by uncover the essence of these different artifacts, whether it's software or hardware. And the hope in the peer community is that all these different things we see in our software, hardware world have a nice theory behind it. And we don't necessarily know what those theories are, but we are trying to uncover those. And we have already done a lot of work in the past. And many of you in this room probably have heard some of the terms that are on this left box. People will tell you, category theory is so cool, you should use that, and there's a universal algebra, co-algebra, inductive, co-inductive types, and classical logic, and so on. So you have learned lambda calculus, you have learned the process calculi, and on the one hand, for people in the system community, it's a little bit daunting to see all kinds of mathematics or theories done in this community. And on the other end, in the programming language community, you see a vast number of programming languages and a vast number of these constructs like static versus dynamic typing, right? Resource manager, garbage collection, effects, encapsulation. I'm basically just listing, the kind of hot topics or languages that you see in today's peer world, in today's software engineering world, or in top POPR or PLDI conference. So that's the charm, right? Because we are trying to understand what's really going on under these complex systems. And the interesting part is that we know that the stuff going on in the right box is kind of partially supported or motivated by the work done in the left box. But peer research has lots of traps and pitfalls. And because the field is so rich that when we work on different kind of problems, we often run into this kind of issues. And in my career of being a researcher in the peer community for the last close to 30 years, I have been running into all these different kind of traps and pitfalls. You develop a very nice theory. It's isolated in its own niche, but real-world system really have many other important issues. We often like to develop a sequential language, have beautiful theory, and then afterwards we say, hey, we need to add a concurrency. And by that time, probably it's too late because your thing was developed for the sequential world and the concurrency does not match very well. And there's a question that under the hood, what are the most foundational things? Should you first have a concurrent code, then you have a sequential code? Or should you first have a sequential code, then you implement a concurrent code? That's the kind of a question that always bother people like researchers. And then you have people saying, pi calculus is the mother of our language, or lambda calculus is the mother of our language, and so it's very confusing as a beginning graduate student, or even for researchers like me, to keep wondering, what's going on. If you have so many different beautiful theory, all claim to be the mother of all theory, which one you should believe? Do you believe Alan Turing? Do you believe Church? Do you believe Gödel? Do you believe some Turing Award winner who invented the denotational semantics and so on? So my tip is you don't believe any of them. You have to only believe your own, right? So you have to really carry a way of, proof carrying certified argument. So when you believe something, hopefully you have a reason to motivate why you believe that. But nevertheless, in the peer world, every year you see all kinds of theories, and you run into this issue. You don't know which one is better. And then, of course, there's also the other extreme, which is you build these languages with the nice concern of supporting legacy system, but often then, there's lots of features that's, very practical, apply to, but it's messy and it's very difficult to apply some of these new principled techniques. And sometimes you develop a language which is very nice for a domain, but it's a little bit too narrow. You have a peer for one application domain. This is nothing to be bad about. If you write a PhD thesis, you develop a language for one particular application domain that you do really well, that's a great thesis. And I have nothing against it. But it does not solve the kind of a problem that I hinted at in my first slide. That is, how do you actually want to reason about a complex system of systems? You could also try to being too general. That is, many of us has at least at one point attempted to define word universal language, right? Universal logic, and without knowing what this perfect language should be like. And then, as PhD students, you could potentially be too ambitious. You develop a new general purpose language, and not knowing that just design the language could take many years. If you want to have semantics, then you have to implement a compiler, you have to build new libraries, and because there's no such thing as a perfect general purpose language, you probably have multiple languages, and then the underlying OS is still written in C, so you have all these interoperability challenges, which is something very hard to address. So while PR research is very charming, it's also have lots of trap and pitfalls. So I claim that the root cause of many of these issues is because the PR research has always been done independent of OS research. The programming language community has been too conveniently ignoring the OS research because they said, oh, I only want to build things on top of some existing OS. Maybe it's Windows, Linux, or Mac OS. And we already have a very nice world of assuming there's a runtime, garbage collector, and so on. So I think that's the wrong approach if you want to solve the challenge of managing a system of systems, because if you don't address those things that's currently dealt with by OS, you are really avoiding lots of hard problems, which could fundamentally change the way you look at the systems. And so my group's research has been focusing on how do you actually leverage these two worlds. And I claim this is a great marriage if you actually think about the problem in a deeper way. Because the programming language, as I mentioned in the first two slides, the very purpose is to uncover the laws of abstraction in the cyber world. If we know how things are abstracted, then you will better understand how different parts fit with each other. And everybody will tell you the general notion of operating system, not a particular OS like Linux or OpenATOS or whatever. OS in the general way is about building layer of abstraction. It's really try to hide these different low-level device or low-level details, and you build these new little abstraction world, and where you can do things in a simpler way. And so that generalized to the future OS for self-driving car, where the hardware platform will be much richer than what we have on your laptop. And it also applied to a world like a blockchain, where the computer is essentially, the world computer contains thousands of machines running similar softwares. So the PL is to use abstraction to reduce complexity, and OS is full of complexity. PL actually depends on the underlying OS for the system libraries. So if you really want to reason about a piece of code written in a high-level programming language, you cannot escape from reasoning about the system call libraries. And you worry about what the underlying OSs do things for you. Another thing that I find interesting is the OS really does a huge set of management of and multiplexing of virtualize these resources, and those have been often ignored by the peer research, but they really should play a critical role. And then we, something surprising to me is that many of the hard problems that we found in programming language research, once you throw OS into the mix, it suddenly becomes easier. You will be finding very surprising. So one example is non-termination, right? The non-termination is kind of the root of many of the complexity of today's language. Haskell monad is cool, but it could still go into infinite loops. And in fact, if you want to define a denotational semantics of a programming language, you build domains, and you have to handle bottom, which often means, sometimes means undefined, sometimes it means, divergence. So divergence causes lots of issues. But in the operating system world, there's really no such thing called divergence. In the kernel, all the code should terminate. Otherwise, it's a bad kernel. At the user level, there's no program that go on infinite loop, because that's like the user program that has timer interrupt disabled. There's really no such thing. So every user program that potentially terminate or potentially infinite loop can only run in an environment that has a timer interrupt enabled. Otherwise, your OS is bad, right? And so you would never hit into any kind of a divergence issues for a language running with a good OS, sitting below. And you would also find that when you try to reason about the correctness of an operating system, type system is not enough. Type system is for people who are too lazy to verify the correctness of the code. If your goal is to verify the correctness of OS, type is a little bit helpful, but it's sometimes is confusing. You really don't need a type. And in fact, in our project, we write our OS code in C. We directly verify the functional correctness. And you will find that we really need a programming language that can write down those types that capture the full specification of the code. That's what we call deep spec, and that's what I will talk about as certified abstraction layer, which actually Ronghui spent a lot of time explaining in yesterday's lecture. So the deep spec Certicos project is all about try to solving this problem of how do we build a really high assurance heterogeneous system of systems. So OS is our major application, but our ambition is really try to figure out when a complex system contains components at a different abstraction level, how do we reason each of these and how do we compose things together? And our conjecture is this is a wide open areas, and now today's PL can handle this kind of complexity because none of the peer provides the support for reasoning about the functional correctness of low-level code at a massive scale. And today's OS scale, operating system today is a pretty, it's pretty limited because it does not have the corresponding language support. So, and in fact, that's why we don't have a really good feature-rich verified OS by now. And in fact, as we're moving towards the future, if tomorrow's OS is going to manage digital currency used to support a self-driving car, then you have to actually prove more and more property. And so you need these new language to support this kind of verifications. So the new insights that, in contrast to the trap and the pitfall slides that I just showed a few minutes ago, is that one of the major mistakes we have made in the peer community is try to handle too many features in the same level. The world is never asking you to design programming languages that handle all these different features at the same abstraction level. In fact, I would argue that what's missing is this key idea of an abstraction layer. That is, any complex system should be always decomposed to these many small abstraction layers, and when you actually work at that particular level, all the things you want to do is very straightforward at a particular abstraction level. But then you have to define what that abstraction level is, and what code you add on that level, and what new abstraction layer you implement. And that's not enough. You need to make sure all these abstraction layers can actually compose together. And by doing that, you avoid solving these problems like, oh, I really need these 5 features to coexist at the same time, and how do you make them to work? And then under the hood, we found that there's actually some kind of a universal or compositional framework for composing these abstraction layers. And that's based on linear logic and game semantics. And indeed, most of the work that we do in Certicos is motivated by this view. And at lunch, I was sitting at the table, we were talking about what is the mother of all logic, right? So Girard, who invented linear logic and of course system F, he is the guy who claims that linear logic is the mother of all logic, right? And I actually believe him. And so the more work we do, we find the connective in linear logic is, linear logic is a paradigm that arguing that the world is concurrent at the beginning. Tensor product is composing these concurrent entity together. And the negation in linear logic has very clean semantics, if you use game semantic models. You don't have to understand what I'm talking about if you don't know anything about the game semantics, but I just want to say that in the deeper peer and logic theory side, researchers have done a huge amount of work trying to figure out what should be done. It's just those part of the research are so remote from OS verification, and most people working on system software don't all the way go to see what's under the hood. And the research we have done in our group has basically been trying to uncover this link. And of course, you have to invent or reinvent and improve these models that we have viewed and really see establish this connection. And what we found is, maybe when we build these things, we should start from a concurrent world. And the sequential code is just a special kind of concurrent code that happen to be, have dependency, forcing these things have to be done sequentially. And that's indeed what, the general direction of my group's research. So the kind of a project that are ongoing, our goal is we try to build a certified system software stack based on Certicos. And at the same time, just like when people write Unix, they invented C, right? We needed to design a new certifying programming language that can be used to write this kind of a certified OS. So that language is called DeepC. It's deep, if I remember, deep specification of executable abstraction. That's what DeepC means, okay? And we want to use this language to write these specifications from which we can synthesize C and assembly code and build OS kernels.